Okay, guys. So we are now recording. Let's get started. Today's Tuesday. We're currently on week 9, and we're doing a lecture today. As you know, this second half of the semester, we're focusing on neural networks mainly, although there are a few algorithms here and there that we're still going to touch on, like support vector machines and decision trees. But the main focus is neural networks. We'll probably start moving into the advanced library, one of the 2 advanced libraries next week, which is PyTorch. But don't worry about it. PyTorch is essentially like NumPy. Like I say, they copy off each other. It's just that PyTorch will bring in some more, more tools, more powerful ideas. All right. So today our discussion we started the perceptron last week. I will give you a homework assignment and time to work on the assignment on Thursday related to the perceptron, so I'll talk more about that. But last week we went over the lecture, like the theory of the perceptron, and then we did the implementation of the perceptron in NumPy and Python from scratch. So today I'm just going to continue driving the foundations of machine learning, the ideas. So you've already seen that we have a function, right? So there's this function, we can call it the inference function, whatever it is, and it can be from the simplest case to ChatGPT. It is the same function. It just gets more complex. It has more layers as it becomes a neural network, a deep neural network, etc. So we'll continue with that discussion today. To kind of motivate that discussion, I'm going to show you, we're going to talk about how we train that model, right? And what does it mean really to train, and how we do those calculations. And your favorite topic, singular value decomposition, is going to come back and make an appearance, so SVD. So we will look at that. And then also the first half I'll do like today, I'll do like the theory. And then the second half, I have 3 Python scripts to kind of help you to visualize and kind of show you how it works. The last one should be a really interesting one. Hopefully, you will like it. We'll see. All right. So you guys are section 3. So let's go there, and we're going to click on content. Table of contents. Okay, so we've covered all of this. Naive Bayes, singular value decomposition. I believe I assigned the homework, or maybe I haven't assigned it, but I provided the information for it. So I'll do that on Thursday. You do have a homework due this Thursday, right? Which is the recommender system. That's due this Thursday. Right, so you can submit that on Thursday, and then I'll assign this new one. Should be pretty easy, to be honest, but we'll talk about it again. So I've gone over that. And then we still need to cover Hopfield networks, but we'll probably next week do this one to introduce Torch. I want to get into Torch already, so we're building up to the competition, if you remember. So I want to assign that soon. Okay, so I'm going to do that, and then we'll take deep dives into the specific other areas of neural networks as we proceed. So let me move this down. Yeah, so that's good. That's good. All right. So today on the agenda then is we're going to go back to this module, the perceptron. We're still not finished with the perceptron. But actually, the thing about the perceptron is like we're looking at all of neural networks, when we look at the perceptron. We're actually looking at a lot of ideas from deep learning also, just on the perceptron. So that's the thing that you have to understand, is that everything builds up from this. So obviously the simplest neural network, the simplest ChatGPT, right, is the easiest one to comprehend. So we're going to, continue here. So last week I went over this link. That was the code. This week I'm going over this one. Okay, so I've already provided all the notes and everything. So We can click on it. All right, and as you can see, during the second half of today, I'll go over these three Jupyter notebooks in order. I have some data that I brought in, should be pretty fun. And then today we are going to go over this, okay? Going back to this function, we keep going back to it, but it is fundamental, okay? And so we are going to essentially go through this and although it looks maybe scary, it's actually pretty straightforward, right? And it should give you some real insight. All right, so let's start here. And I will start, so this is sometimes called least squares. The problem set up here is, what do we want? We want to build an AI. You want to build a model, right? So what is a model essentially? What's ChatGPT? You give it a question, it gives you an answer, right? So you give it an input, and it gives you an output. That's essentially what it is. So you can encode the question any way. We've seen already an example at the beginning of the semester where we encoded sentences, right, in a very simplistic way. Obviously, ChatGPT uses something like that, a little bit more advanced, but same idea. So at the end of the day, any neural network or AI is just this formulation. We just build from here by adding steps, layers, etc., but it just builds from that. So essentially, we can start and assume a linear relationship between an input, and this idea, right, of linear and nonlinear comes back again. And it's going to be a consistent theme that we're going to explore. And hopefully, this lecture is meant to give you a lot of background, but also drive that point of linear versus nonlinear further. So we assume a linear relationship between an input x, a true weight w, and an output y, right? So we're trying essentially, usually when we get the data, we have an x and a y, right? That's what we have. We split the data, train, test, right, and all that. But as you know, what we're trying to learn in these models is this w, where this w could be a variable, it could be a vector, and so I have a couple of examples of that today. All right, so that's essentially what we're trying to do. So where we know that x is the input, w is the unknown scalar parameter, some kind of a thing that has to be learned. Remember, those are called essentially the weights and the parameters as well. Y is the observed output, or the thing that we want to predict. Notice here I've added this little term here, noise. Don't worry about it. It's not the same as bias. So usually I'll write this on the board, but this would be y equal wx plus b plus e. So what is the e? You guys are cybersecurity students, so you're used to this concept in networking, right? You send a signal, right? And you have to do what? Checksums and all that, right? And what was the purpose of that? You know that as the signal is going, the zeros and ones are going through copper, what might happen? Noise, right? There's some kind of noise deterioration. So that's just what this represents. We always have this assumption of noise, and I'll provide this in an example later today. But don't worry about it if it's confusing you, right? It just means that some of your samples, right, have a little bit of noise. So then today, let's switch to the whiteboard. I'm going to introduce something very fundamental as we start. So we have essentially two steps. We have like a duality or two things in AI and machine learning, whatever it is. And so the two things, I'm going to essentially like do something like that. And you guys can see the whiteboard now. All right, let me switch to red. So we have two functions in machine learning. Okay, that's important that you guys visualize that. We have two functions. They can have multiple names. In general, we're going to call one the inference function, inference, and the other one we're going to call, and this is one of the reasons why I've given you the perceptron homework, because you actually, use the inference in training, but the thing that gets deployed is the inference function and not the other one. The other one that I'm introducing today is sometimes called the objective. The general term that we're going to use for this one is called the loss. And what is the loss? The loss is the objective, the way that we train this one. Okay? So what is this one in its simplest form? W x plus b. Do you guys see that? The line equation, okay? We can add lots of things to this. We've already done that. Like, for instance, in the perceptron, we said that we would rename this z, and then we run this through a step function, and now we can calculate y, right? So we've talked about that. But that's, as you can see, that's what neural networks are. You're just adding more to the original core, but this original core does not go away. In fact, in PyTorch, although you won't see it, we're going to have this essential function called NN linear. And then that function, I'll explain carefully, holds this machinery inside of it. Okay, so that's essentially the idea. Okay, so I'm going to go back to its super simplest form, which is this one. And notice I was adding this idea of noise as we will be using it today, but you can also disregard it if you'd like. So the essential thing is in a supervised learning problem is that you have y and x, right? You have these values, but you do not have w and b, right? These are unknowns. These are the learnable parameters, the weights and the biases. We saw last week that the perceptron had a rule, right, on how to update the weights and learn them. So that's essentially the key problem. We need a way of learning this law, this W and B. So how do we learn it? So that's where this side comes in, right? So we're going to see that there are many ways in which we can learn it, right? So that's the other set of equations. So those equations can change, but in general, that's why we're just going to refer to them as something like J or the loss, and then we figure out what it is that we're going to use, okay? So in the perceptron, what did we use? We used something like this, right? Xi, if you remember, and some kind of a parameter here. This was essentially the update on how we learned the values. But as you can see, this is actually very specific to the perceptron. I'll show the derivation of this a little later as we start building up on these ideas. But essentially, the core of this, if you take out this and this, is that you are essentially comparing what? If I now, I'm going to erase this part. If I now just add this little hat here, then that means essentially that I'm learning, right, the predicted minus the real. So you're always trying to do this as a type of a loss function, this comparison, right? And this can also be called the error. Okay? The error. Do you guys see that? So there's essentially two functions, right, that we're going to have. Usually this function is the one that we're trying to learn, the model, the intelligence, right? And this is just how do we learn it? Either through the perceptron rule, as we have seen, a more generic one, notice that I'm squaring it now, for instance, right? Or is there another method to learn the weights and the biases, right? So how do we learn the parameters? Well, as it turns out, there are two ways, essentially, that we can learn this function over here, the parameters W and B. One is going to be the classical method, actually, right? And one is going to be an iterative approach. So iterative is what? The perceptron was iterative, right? Right? You guys remember the perceptron was iterative. We already did this. All of neural networks, all of ChatGPT, deep learning, everything is going to be iterative. So all of modern AI is iterative. However, in the past, not in the past, but I should say, the classical method, there is another way. And that's the classical method, which is actually based on singular value decomposition, or it's called the analytical solution. the analytical solution, okay? And so I'm going to talk about this one today just to show you that actually, and we'll prove it with our Python, right, that there, it used to be that we could calculate the W and the B without using the iterative approach. Do you guys see that? Instead, we use what is considered a more well-founded mathematically approach. So you can see how scientists, mathematicians, etc., would prefer this one over this one, right? If you have one that, first of all, you don't have to calculate it via a loop. It just works in one shot, and you have some equation that you derive from somewhere. Wow, right? And everything is explained clearly. That is definitely the preferred method, okay? We have this other method, as you saw with the perceptron, where we have to kind of like try and keep trying and keep trying, but in a smart way until we finally arrive at the results. So as it turned out, so you guys see this, right? So we have essentially one function that we're trying to train by learning the parameters, and then several ways of learning it, right? We've learned iterative, perceptron. We will spend most of the semester in the iterative approaches, but today I will show you the other alternative called the analytical solution. So if we look at the timeline, let's say I'm using kind of my own estimated date here, but around 2012, right? So before 2012, so before, like way before, like the 1980s, let's say, people for sure in industry everywhere, they were using this equation because you give it an input, it predicts, but they were using the classical analytical solution to solve it. Do you see that? Classical. But as you can imagine, during this time also, data is growing, problems are getting harder, right? Computing power is improving. So people, start thinking, well, classical, maybe it's not enough. We need to use the iterative solution, something like this. Like the perceptron, was created around 1949. So the idea existed since then. Do you guys see that? So essentially, the problem with classical, and I've said many times about this, in AI, things become important, then they're replaced, and then they come back, so you never know. So it's going to be some clever person later that's going to figure something out. That's what breakthroughs are, right? But as it stands right now, the limit of the classical method is going back to that same idea of the donut, right? Linear models versus nonlinear models. The classical method is for lines. It predicts a line. It doesn't have the capacity to predict like curves and polynomials, quadratic, even further. Those are complicated, but no one has figured that out yet because there's more options, let's say, for those kinds of things. But the solution of the classical method for linear models is great. So what that means is, remember this, right? We'll come back to the XOR example. It'll take a while to talk about XOR, but we'll come back to it. Remember, we can't because we need some kind of a curve, right, to have a perfect classification. But there's tons of problems out there that are linear, right? So, lots of problems. And so the data that we used on Tuesday for you guys, last week, on Tuesday was linear, right? Because we obtained good results. Do you guys see this? So, classical is pretty good for this. Classical is pretty good for this, okay? So here we have then, and for this kind of problem, the classical method just couldn't really figure it out, so we needed to add more like iterative processes and more nonlinear techniques. However, we have talked a little bit about support vector machines, right? And this is a good opportunity to go back to that topic. Why was support vector machines so important and profound? Well, around the time of, let's say, around here, between, let's say, the 80s, 1980s, and 2012, some very smart person, Vapnik, came up with this algorithm called support vector machines. Kind of with the same obsession of the people here that wanted to continue using the classical method. Why? Because it's robust, well-founded, highly studied. You can derive the solution mathematically, not like for loops and iterative processes, which almost seem like a black box, right? It's like try this, like that. So this is the reality. People resisted because of this. Vapnik created support vector machines, and now people were very happy because, before they have this problem and they can apply the classical method, support vector machines, and they were really happy about that, but they couldn't apply it here, so they were frustrated, right? And so they then had to try nonlinear methods, perceptron methods, iterative methods. But Vapnik does what? Adds this idea we need to cover, when we cover support vector machines, we need to talk about something called the kernel trick. That increases the dimensionality, remember that? And by doing that, we now can project some of the values right over here. Okay, so these are no longer inside. So guess what? Because of this, this data in its higher dimensional space is linearly separable. Do you guys see that? And once again, the classical method will work here. The well-founded, great idea will work there, and it's really fast. All you have to do is this little trick of mapping to higher dimensional space that we will learn about later, called the kernel trick. So this really excited people because now even nonlinear problems could be solved theoretically. It was very nice and well-founded. But then, of course, we have this explosion in data around here, GPUs around 2007, and at that point, it just became more practical. These just totally dominate the iterative algorithms. Do you guys see that? And so we needed to have a robust algorithm in that space, and that's where stochastic gradient descent comes in. Believe me, this will be our focus of discussion from next week until the end of the semester. There's only one algorithm, surprisingly maybe to you guys. So, but yeah, this is kind of the evolution. So inference methods, tons of them, right? Perceptron, multi-layer perceptron, deep learning, lots of variations there, right? And there's other kinds of architectures. But as far as, so there's many, so let's say many approaches. But it might surprise you, but when it comes to learning the parameters, right, there's fewer. There's the classical method. I've discussed that. But really, the classical method in modern applications cannot beat stochastic gradient descent. And there is only one approach. There's variants of it, but the main algorithm, the main idea is only one. So our neural networks in this class will be trained with stochastic gradient descent. ChatGPT is also trained with stochastic gradient descent. Do you see that? There is no other. All right? So we're going to start learning about it. Okay? But just keep in mind, at the end of the day, the focus is still learning these parameters. Got it? Everyone with me? All right. So then, now that we've discussed this, let's look at the formulation. So essentially, the formulation is that you have an objective of a function. And let's keep it super simple. Wx, no bias, no anything, right? We have the y and the x. We need to learn the w somehow, okay? So how do you do that then? That's the inference function. And we need to have some kind of a formulation that we want to minimize the error between the predicted and the real. Do you see that? That's essentially the whole formulation right there. We want to learn, and remember, this is some kind of an error. So that's why it's minimized, right? So we want to minimize the error. What is the error? The difference between what this predicts and what this gives you, with the real value. Got it? So from here, then, is where from this same formulation is where we start. We start to try to figure out how to do things. And people propose algorithms, but other very smart people just said, you know what, I'm just going to look at this math, and I'm going to start, and we'll look at this possibly on Thursday, this part, but the people just look at these two ideas and start, let's solve this, right? Let's solve this as a set of equations, okay? And so essentially they did some derivation and calculation of this, and they arrived at an equation, which I have here. Here, all right, so I've set this, and let me actually. Okay, right, so they have that. And what I'm writing is here, the matrix form. So we rewrite the system. So let me write it like this, okay, which I was doing that. So let me move to a new page. So they write a system where the goal is we want to make predictions based on this, right? That's what we want. So the way to solve it is that we want to figure out that W, right, that we minimize some kind of a difference between, and let me add a little hat here, y hat minus y, and then we can square it or not. It doesn't matter. So it's just some kind of a difference, some kind of an error. Additionally to this, if you notice, what is this y hat? Is this one? So essentially, we're saying that we take xw, right? Oh, this is not hat. Y, which is the real value. So you can see essentially that we have we're comparing the real to the predicted, and the predicted is dependent on the x's and the w's, okay? So from here, they did the derivation of all this information, and they arrived actually at a single solution called the analytical solution. So the derivation of this is outside the scope, but just keep in mind they derived it, and so they called it the analytical solution. So that's why this is so highly regarded. And the analytical solution is W is going to be equal to, remember, X is this, right? X is this matrix in this case. So let's do the solution X transpose X minus 1, which is the inverse of X transpose times Y. So how incredible is that, right? That they formulated this problem. We're trying to create this function. We want this W. This is essentially the problem we have. We have to compare the predicted with the real. They do the math here, lots of math, like algebra type of thing where you rearrange terms, cancel things, do conversions, and they actually arrive at this, a single analytical solution. So as we will see in our code examples later, No loop is required. No update rule is required. Essentially, we just grab x. Do we have x? Yes, right? We have x for sure. Do we have y? Yes, we have y. So we can from there learn w, and then once we have w, we can use it for new data, new samples, the test set, etc. But we are able to analytically learn, or calculate, I should say, because we're not, calculate the w. So this is why, this is the reason why people were so obsessed and so resistant to neural networks for the longest time. Because since you saw from the lecture last week, right, the perceptron algorithm requires this loop and an update of some equation. And where did that equation come from, right? So I'll demonstrate that later. But whereas other people said, I don't need that. I just need the data y, I plug it in here and calculate my weights, and now I have it, right? I've learned the weights, and that works perfectly. Does this concept make sense, guys? This is like, the essential idea. All right, so if we go back then, so now we've arrived at this. We have this equation here, this formula. So let's go back to sharing. All right, so we've done that. The analytical formula, right, is like this. But there's a problem. Okay, so they were excited, and you'll see this formula used sometimes, but oftentimes you actually see it instead written in terms of something familiar, the terms from the singular value decomposition. Okay, so as it turns out, this formula is a little finicky, right? But people did some research. You guys already know what SVD is, so the formula fails if this term, right, is singular or ill-conditioned. And what does that mean? It's just a fancy term for the following. So the normal least squares formula only works when the matrix you need to invert is well-behaved. If the input data contains features that are duplicated, highly correlated, or almost linearly dependent, the matrix becomes singular, which means it cannot be inverted. So you guys know what correlated features are, right? You've seen this before. So if you have iris, petal length, petal width, sepal length, sepal width, do you think those are totally independent? I mean, if you look at a plant, right, and if you look at a leaf that's very big, you can assume that the other ones are also big, correct? Or other aspects of that plant are big. So you can see then that they are always correlated. We talked about this in naive Bayes, right? One of the weaknesses of naive Bayes was that you had to assume that the variables were what? Independent for it to work. Do you guys remember that? That was an important little insight. But most things in the world are going to be correlated. Just look at language. The furry cat. They're going to be correlated, right? So that's the idea. So essentially this was saying, okay, the data is too correlated. But we learned already of a technique that helped us to break up, right, our matrix into other matrices, and where we can actually look at more data, right? And that was the singular value decomposition. So that's what this is saying. So this fails when it's duplicated, highly correlated, almost linearly dependent. So it becomes, it cannot be inverted. Or it's ill-conditioned, meaning it can technically be inverted, but produces unstable, widely inaccurate results due to numerical instability. In these situations, even tiny amounts of noise or rounding error can cause the solution to blow up or become meaningless. This is why practical systems avoid directly using the normal equation, this one, right? So maybe you're one of these people building these models and you were highly disappointed by this, right? But then other smart people came in and they figured out, there's a solution, okay? So this is why practical systems avoid directly using the normal equation and instead rely on singular value decomposition. So essentially now, because we use those matrices instead, you can derive the formula even further, which produces stable results even when the data is poorly conditioned. Do you guys see that? And so once again, we go back to the topic of singular value decomposition, which you can see is so important in machine learning, classically and otherwise. And so, we're going to look at it. All right, so we're going to look at singular value decomposition. So I'll show you this one just to kind of give you the intuition. So it's US. So you guys remember, right? We already talked about singular value decomposition. What did we say about that? Exam type question right there, right? Any matrix that is m by n can be decomposed into three matrices that are U, S, and V, where S is diagonal, right? And we looked at the example of recommender systems, which is actually your homework, right? And we looked at how from movies and users we could get what? Movies and genres, right? Concepts. So if you remember that. So that's what this is doing. So essentially then, we can say X USVT. So let's switch to the whiteboard. Okay, so we are here, and we know from singular value decomposition that X, the same X, can be decomposed into U, S, V transpose. Do you guys see that? That's how it works, right? We have a function in NumPy that gives us this. And then, believe it or not, this idea then you just plug in. So you just replace. So now people start doing the derivations, they do simplification, proofs, and math. But essentially it comes down to something like this. Transpose, then USVT, this is like that, -1. This means the inverse. We'll actually do this in NumPy. We just invert the matrix. Then again here, USVT, T, and then RY. Do you guys see that? That's essentially what they're doing. Like the math, like the same algebra that you guys did before, right? Rearrangement of terms, cancellation of terms. There's going to be, all kinds of rules, right? So you can say that these become transpose, and then this one becomes normal, right? So this one becomes U transpose, S transpose. This, because it's 2 transpose, actually becomes just not transpose. You see that? So essentially, this is the process, okay? I'm not going to ask you to do this in the exam or anything like that. It's mostly just to show you, right, how things go and where they come from. So at the end of the day, then, they do all the calculations. So I'll just do like ... They do the derivation, and we will arrive at a new formulation for W that is going to be written in terms of singular value decomposition, which will give us a more stable solution. And once you have that stable solution, you're in business, right? So you can now apply support vector machines. You can, if it's a nonlinear problem, and if it's a linear problem, you just use as is. No iterations required, none of that, right? And this is even today used. So machine learning, you can go to a factory at US Steel, and I guarantee you that there's a couple of systems that just rely on this, because not everything requires a bazooka, right? Sometimes something just requires a little hammer, right? And so it just depends. However, when we're talking about massive AI, large language models, those kinds of things, then these methods, at least so far, right, aren't the method for learning. We have to go back to what? The iterative processes, of which we're going to spend several weeks understanding how those work. But still, it starts at the perceptron. Do you guys see what I'm saying? Does this make sense? Are there any questions? So you can see the evolution and how important this is. Someday, as somebody, let's go back here. It wouldn't surprise me at all, not at all, if someday somebody takes the formulation that's iterative, right, for training ChatGPT, and they do some crazy math, and boom, they arrive at an analytical solution that is almost as good. Do you see that's how it works? But so far, we don't have that. We still rely on the iterative process. So here is kind of the derivation if you guys are interested. So remember, we said that this one is not so stable, but it does give you W. So you can try it. Sometimes because of your data, it's not great. But if you use the singular value decomposition, which you guys are familiar with, then now we start to derive it here, and we arrive at this solution. That's actually the solution that we will implement in our Python code today, and it'll be pretty easy. One line of code for SVD, we get those matrices, boom, calculate W, okay? So just keep that in mind. So actually, if you notice, I already wrote it down here in Python form. So what is the solution to, after you do all that rearranging, right, the weights become V, the diagonal inverted, U transpose Y. All right, so I'll write it on the board. Oh, no, wait, I have it on my, that's why I opened this. So that solution is that one. So let's go back to the whiteboard. Okay, so we were talking in the previous slide, right? So this one doesn't work, but we know the singular value decomposition. Essentially, we plug in the values, do a whole bunch of canceling, rearranging, all like normal algebra, just in the linear algebra context, and we arrive at, and I'll use a different color for this one. We arrive at W, we're calling it W tilde just to mean that it's like an approximation. V, S inverse, U transpose, and the Y. You can see it looks a lot like the first one, right? But instead of the X, we just use the equivalent singular value decomposition of it, and that's it. So once, and the code, which is really important that you guys look at, it's going to be W, let's say, tilde, VT. So the equation is going to be like this, if you notice, VTT. Why? Because the SVD actually gives you the V transpose. But in this formula here, the V is not the transpose, it's just a normal V. So we have to take VT and transpose it, if that makes sense. Hopefully it'll be more. So like when we take in the code, we're going to take the SVD of X, and it should return something like U, S, VT. Do you guys see that? And so, but the equation requires not the V transpose, just a normal one. So then we just transpose it again. And then this symbol, which you will start to see more and more of as we start moving into PyTorch, is the matrix multiplication. Remember the dot product, right? So we've talked about that. Then in the code, remember that when we take the SVD, S is not a diagonal matrix. It is just like a list. So for what I mean by that is, 1, 2, 3, 4 in the diagonal, right? And 0 elsewhere. So S just returns a list of 4, like a vector. So we actually have to diagonalize it. That's why we're going to have in the code np.diagonal of S, and that just means that we go from that to that, so that the matrix multiplication can happen correctly. Then this one needs to be not S, but inverted S, right? The inverse of it. So we are going to invert it by saying numpy, and I'm using shorthand here, numpy inversion. It should say linear algebra. Okay, and then let me actually. Do you guys see that? And then the next one is UT. So that one, we just take this U. Remember, this is the matrix multiplication symbol, U, and we make it U transpose. Why? Because this returns U, but the equation came out when we rearranged the terms to UT. And then the final parameter is Y. Do you guys see that? So essentially, these 2 lines of code should be amazing to you, right? Because I could give you a problem right now, any problem in machine learning, right? Where I give you some data, your X and Y, your familiar X and Y, and I tell you, train it in 3 seconds, right? Whoever does that gets an A in the, you know what I mean? Like, all you have to do is take that X, run SVD, get USVT, then know this formula, plug it in like that, you got W. And now that you got W, what can you do? Right? You've got W, so you give it a new X, you can predict. That's kind of the great idea, right? Unfortunately, if we get into the XOR problem, right, the donut example that I've been talking about, performance may not be so good, right? So it's going to go down. But there's going to be a lot of problems out there in the world that solves it. All right, so for this class, I really don't spend too much time on the analytical solution except to use it for you guys to understand it and motivate it, right? But as you have seen, the other approach is the iterative approach of updating the weights, and we're going to spend a lot of time on that one as well. Guys, are there any questions on this idea? No? All right. So, but yeah, a lot of very smart people worked on this, and this was machine learning, essentially the classical machine learning for years. All right. So now, let's go ahead and go back to those slides just to finish. All right. You can see we get this other formulations of the inverse that like there is instead of writing, I prefer to write out the equation. That's just my preference. But if you don't want to, you can just use the NumPy function that does this too. I mean, there should be the same result. Okay? And that's it. So interpretation in machine learning terms. This is the simplest possible supervised learning model. So I could ask you this on the exam. What is the simplest possible supervised model? Hint, not iterative, right? Something like that. And then you can say, well, it's when we formulate this, training means recovering the parameter W, like this with this idea, but here you solve it analytically, not with gradient descent or even the perceptron update rule. Okay, which is, I think all of that is pretty intuitive to you guys except for one little aspect of it. Okay, now, so remember the derivation. Now this part, I leave it to you guys just for fun. If I recommend that you try to do this just as a fun exercise, but it's not homework. It's just essentially the whole derivation. So you can see this was, like to calculate W, you know that the singular value decomposition is this one, so you just substitute X with that. You can see you plug in the values, and then this will show you all the operations that go into it until you arrive at the final solution. Got it? So just something fun for you guys to try out instead of going out on a Friday night. All right, so now that's it as far as the lecture with the analytical solution. So hopefully that motivates you. And this is pretty fundamental, as I've said, because there was so much resistance, right? People would say, oh, this is mathematically beautiful. Neural networks are ugly because you have to use a for loop and update things in a strange fashion. Do you see that? So that has always been. But at the end of the day, the iterative processes have won, at least in the last couple of decades, and they have led to, well, you guys are living through this world, right, of artificial intelligence. All right, so we'll go back to these ideas later. So one last thing I want to do is the following, and this we'll touch on a lot later, but I want to tie, oops. All right, so again, you usually have then an inference function, of at least the form like that, right? But it can be much more than that. And over here, we're going to have some kind of a loss function, right? Which could be the analytical solution. It could be the perceptron rule. But at the end of the day, the more generic way of writing this is going to be, and I should say y hat minus y, and usually squared or something like that. And remember, this gives you the understanding that it's some kind of an error. So if it's an error, you want to minimize. So you minimize this error, okay? So as we start moving forward, you will learn that this is actually another function. So there's actually always going to be this idea, this duality of two equations or two functions, right? This one is the neural network. Here it's basically a neural network with no layers, no activations, no nothing. Just a matrix multiplication, and that's it, a dot product, right? That's it. But this can scale up significantly. So for the rest of the semester, even starting next week, we'll just start exploding this function in size, okay? And that's a neural net, right? So interconnected functions, okay? This function, you guys now that this is an important concept. Just like there's two equations, right? There's also two plots that live in totally different vector spaces. They're related, but they're not in the same. It's like this dimension and this another dimension, right? They're related, and this is something that is cause for confusion, so I want to stress this. So you see me write this a lot, right? So, and let's forget about the donut example, let's just keep it simple, right? So what do you guys know? This is the space of the features, right? Feature 1, feature 2, and your data, sepal length, sepal width, right? And you have your x's and your y's. This function here is doing what? Creating a line, correct? Maybe it's a line that fits through the data, or it's a line that separates the data. At the end of the day, it's a line. I can flip it however I want, right? But it is a line. Do you guys see that? Does this make sense? There's a second graph, and this is the new graph for you guys. So let me erase this little part here. And now let's just focus. You agree, right? That you look at this function and it creates something graphical like a line. We've learned this in school. I'll demo this in the code in a second. But that produces that line. So you would agree that this is, y equal x times w, a function, creates something graphical. So this one, j equal this, also should create something graphical. Do you guys agree? So it does, in fact, do that. So if I do this, for instance, this is just a difference. So essentially an error. So if it's squared, it looks like this, right? So if I have then replace it with x instead, what happens? It just takes anything and squares it. So for instance, I could draw, let's say that I'm drawing like here, right? So I have x minus 1, or x1. What is that squared? 1. Negative 1, 1. Do you guys see that? What if I replace it with 2? So plus 2 is 4, correct? So 4. So do you see how it looks like that, right? So if I select minus 2 square is what? Come on, guys. You can speak. Huh? Minus 2 square? 4, right? Yeah. So 4. Do you see that? So it creates, this function here does create a shape, correct? This one in a space, this one in a space creates a line. This one in a space creates this curve, right? This is called a quadratic function. Sines create these little weird things, and cosines, and right? So we know this, right? So that's intuition I want to give you. So understand that I'm able with this function to create something like this. Okay, great. That's established. And my battery's low, so give me a second. All right, so now, since we established that that can create that shape, now let's look at the actual J function and what it means, right? So here I'm going to create another plot, a second plot related to this one, but not in the same space. Now, because I know this looks like this, essentially I can draw that there's a curve, a quadratic function, a bowl, something like that. Another thing that we're going to look at is I'm going to change the term J to cost, okay? Cost, error. You guys agree that it's the same meaning, right? Cost, error, whatever it is. You want to minimize your cost, right? So you guys want to minimize your expenses, your costs, the same as you want to minimize your errors that you make and things like that. So we're going to say that there's a relationship between cost and the values on this side. Y is just a real value, but we know that Y hat is what actually? XW. Do you guys agree? Does this make sense? XW. What's important here is there is a relationship between cost and one of these variables. X and Y cannot change. They're not variables, right? They are constants, essentially, your real data. What's the only variable here that changes during training? That would change during training? The weights. Do you guys see that? So this function has this representation where this side is cost, and this side actually can be written entirely in terms of W. And why is this important? Because obviously, let's see if you guys agree. Let's say that I have a really bad weight, like a really terrible weight, right? And I predict something, and it's way off from the real value. So this difference, would you agree that it's going to be really high, like a really high cost? Do you guys see that? It would be a high cost. So let's say that's a high cost. Now, because all these parameters only live in this equation, that means that in this space, the points only live in this curve and nowhere else. Do you guys see that? And so now, cost will hit this, and now it tells you that this is the W. Do you guys see that? So what if so I have W1, right? I'll ask you this question. If I want to minimize the cost, and I can only move on that curve, what do I do to W1? So which option should I try to implement? W1 minus 2 or W1 plus 2? This, of course, goes from 0 to infinity. Which one would be the approach if my goal is to minimize cost? Yeah. Plus 2, exactly. If I do this, then W1, let's say W1 is 1 here, plus 2, maybe it comes to here. Now it's W3, correct? So this might be like W1, this is W3. So, do you see that? This W tells, minimize the cost. So this is really important. So this loss, we use it to figure out the set of weights that will minimize the cost. Do you see that, guys? What if you had picked something not minus 2, not plus 2, but plus 20? What could have happened? It could have gone to this side, right? And maybe actually, if W1 22 is here, guess what happened? right? That was too much of a change to the W, right? And so it increased the cost actually. So do you guys see this relationship? This is really important, right? This is how, I'm just giving you right now a hint, right? That in the future we'll use this function to update the W's. If we add too much, the cost goes up. So we want to somehow figure out a way that when we're here, we need to efficiently and maybe stop like right there, right? Would you agree? This might be like the optimal W. We do not want to continue in that direction because we would actually increase the cost or the error. Got it, guys? So this is all. I can leave it here for now, all right, because this is actually what's coming up. But the key thing I wanted to say is there's two functions, this one and that one. And these two functions can create shapes. This can create this line, right? Later on, we'll see, we can modify it to create other curves. And then this one creates this little thingy here, this curve, a bowl shape. And the key thing is just like this one maps from F1 to F2, this one will map from J or cost to the W's themselves, right? And so now you can see that by modifying those W's, we have a way of measuring if the error went up or down, because when we move in this, we can only move according to this curve. The rule here enforces that. Like we're locked in. There's no other, those are the laws of physics there. Any questions on this idea, guys? So again, this is just an introduction. Take from it that we can create this shape from here, and it's not the same space as this one. Okay? Got it? Any questions? All right, so that's the theory for today. We're going to switch over now to the code, Jupyter Notebooks. In particular, what I want to implement, so let me go over here. I want to implement, where was it? This, right? I want to implement this. I want to show you guys that I have a X and Y, just like you've had always from day one in this class, right? You have an X and Y. You want to learn the W's or some way, so that when you have an X, you can predict Y, okay? But to solve for W, we're going to use the analytical solution, and in particular, the stable and singular value decomposition-based solution. Got it? And this will actually bring in a lot of ideas about lines and how they work and so on. Okay? All right, so I'm not hearing any questions. All right, make sure to read through this, okay? Go make sure you understand this concept. All right, because these two things are related but kind of slightly different scope, I'm going to end this video here.